If you have ever watched a skateboarder launch off a ramp and spin a full circle in the air, you are already familiar with measuring a turn. We call that full rotation a 360. If the skater only makes it halfway around and lands facing the opposite direction, we call that a 180. That half turn forms a perfectly straight line. We use the number 360 for a full turn all the time, but there is no mathematical law that requires it. Dividing a circle into 360 tiny slices is a purely human invention, a convention dating back thousands of years. Since 360 is an arbitrary human language for turning, you might wonder if there is a natural language, a way to measure a turn that comes from the physical world itself. To find that measurement, we have to set aside our familiar degrees entirely. We need to look at the geometry built into every single circle. Whether looking at a tiny coin or a massive orbit, every circle is a perfectly scaled copy. Because of this, dividing the total outside circumference by the diameter across the middle always gives the exact same number, every single time. Long before modern calculators, ancient builders and astronomers noticed this stable pattern in their physical work. They saw that the boundary of any circle is always a little more than 3 times as long as its width. Early mathematicians, like the Greek scholar Archimedes, worked out methods to calculate this constant ratio with incredible precision. Because this ratio applies to every circle in the universe, it deserved a name. Mathematicians agreed to call it pi. We are often taught to memorize pi as the decimal 3.14, or told to press its button on a calculator. However, pi is an exact physical measurement. The total circumference of any circle is exactly pi times its diameter. This diagram shows what mathematicians call the unit circle. It is simply a circle with a radius of exactly 1. If pi dictates the rules for all circles, this is the easiest place to see those rules in action. If the radius from the center to the edge is 1, then the entire line across the middle is 2. Since the outside distance is always pi times that middle line, the distance all the way around this unit circle is exactly 2 times pi. Imagine a point traveling 1 full turn along that outer edge. By the time it ends up exactly where it started, it has traveled a physical distance of 2 pi. Now, think about making just a half turn. If the entire trip around is 2 pi, we can simply divide that distance by 2. That means the outer path of a half circle is exactly pi. On a unit circle, if you trace your finger along the curve from one side to the exact opposite, the length of that physical arc is not a random decimal, it is exactly pi. Measuring a turn by its outer distance leads to a unit of measurement called the radian. As you might guess from the name, it comes directly from the radius. Take that straight radius line of 1, bend it flexibly, and lay it flat along the curved outer edge. You create an arc that equals the exact length of the radius. The interior angle created by that single slice is exactly 1 radian. We found the half circle's total outer length is pi. So how many of these curved radian slices does it take to get halfway around? It takes 1, 2, 3 complete radius lengths, plus a tiny fraction left over. Exactly pi radians. Radians do not rely on a number chosen by humans. They use the circle's own internal geometry to measure turning. Let's look back at that basic half turn, the one that creates a flat, straight angle. This diagram shows the direct translation. In our conventional human language, we call this straight half turn 180 degrees. In the natural language of the circle, we call it exactly pi radians. They are 2 different names for the exact same amount of turning. Degrees work perfectly well for building a ramp or describing a skateboard trick. But advanced mathematics, like calculus, relies on radians because they directly connect the amount you turn to physical distances, like the radius and the arc length. The rule that 180 degrees equals pi radians is a logical fact of geometry. You are simply reading the natural language of the circle, translating itself.